طيب بسم الله الرحمن الرحيم. So last time we started to talk about digital transmission. We said that digital transmission is when we actually convert the digital data to a digital signal and then we transmit it as is over the line. And we talked about these very important criteria or matrix that we will use to evaluate the pros and cons of each of the line coding schemes. We talked about baseline wandering, DC components, and the self-synchronization. The first two are phenomena that really deteriorates the performance. So baseline wandering happens if the baseline wanders up or down, in which case it actually increases the probability of error. And DC component happens when we have very high power at zero frequency. So if you have zero frequency component in the line coding scheme with very high power, that's when the DC component happens, and that's really bad. And that also deteriorates the performance, because any low pass filter you will use will have very low efficiency at very low frequency. Self-synchronization on the other side is good. It's good to have self-synchronization. However, if you have lack of synchronization, then you increase the probability of error. So we will take these as the baseline, as the main criteria to evaluate all the line coding schemes that we will talk about. So the line coding schemes are categorized as follows. You have line coding schemes that lie in the category of unipolar, and by that we mean that the line coding schemes will have values either in the positive side of the voltage or the negative side, but it does not have both. Okay, so it's either on the positive side or on the negative side, but it does not have both. So when we talk about positive or negative, the zero is included. So either positive or zero, okay, or negative or zero. And of course, the clear example for this is non-return to zero, which we are all familiar with. So if you have a non-return to zero, usually we use positive voltage to indicate 1 and zero voltage to indicate 0. We can select to use negative voltage to represent 1 and 0 voltage to represent 0. But in all cases, you cannot have both, positive and negative. Polar, on the other side, talks about the fact that you have positive and negative, but not 0. So here we have we have both positive and negative, but we do not have 0 voltage. If we happen to have 0 voltage, as we will see, it's not meant to represent data elements. It's not meant to represent the data elements, as we will see in a minute. Okay. So in that we will talk about many line coding schemes like polar non-return to zero and the return to zero and the biphase and so on. The bipolar the difference is that it talks about the fact that we use a positive, zero, and negative all at the same time. Okay, and the zero here is to represent the binary bits, or to represent the data elements. So the difference between polar and bipolar is the fact that bipolar uses the zero to represent data elements, as we will see. So all of these line coding schemes categories, they use a positive, negative, or zero voltage levels. The multi-level bar, on the other side, it uses arbitrary number of levels, as many levels as you want, and for each of these line coding schemes you have number of levels for the voltage and number of data elements that this voltage level can represent, and so on. As we have discussed before, you can use for example 4 signal levels to represent 2 bits at a time. Okay, this is what we talked about for Nyquist, right? So the signal rate or the bit rate for any transmission line is proportional to log 2 of L, as we have talked about before. So by increasing the signal levels, you can increase the bit rate, and that's what Nyquist told us. The multi-transition is a very interesting category where the absolute voltage level does not indicate the actual bits. So if you see the voltage level positive or negative, that does not indicate that this is 1 or this is 0. What actually represents the data elements is the transition between the voltage levels. So this is where the information of the bit is. The transition between the voltage level is the indication for whether this is 1 or this is 0. So multi-transition here talks about the fact that we have different types of transition between positive, 0 voltage, negative voltage, and each time the transition indicates 0 or 1 or 0, 1 or something like this, as we will see. So we'll talk about each of these categories in details, and for each one we have the three main criteria that we talked about, which are the baseline wandering, DC component, and the self-synchronization, in addition to the complexity that this line coding scheme indicates or represents, as we will see. So, for example, non-return to zero. Non-return to zero, we know that non-return to zero is the simplest. So one of the pros of this is that it's simple. Okay, here R is equal 1, right? So R is the ratio between the data elements and the signal elements. So we have one data element represented by one signal element. So 1 over 1 is 1. So R is 1, which means that the signal rate is C times N times 1 over R. Remember this equation? So C, as we said, in most of the time is 1 over is half times N times 1. So it's actually N over 2. And this is for 2 voltage levels. This is actually the minimum according to Nyquist. According to Nyquist, as we said, the maximum bit rate that we can achieve for any transmission line with bandwidth S or with minimum bandwidth S, it's actually double the bandwidth. Okay, which means that the signal rate or the rate of change or the maximum frequency is actually N over 2, and this is limited by the Nyquist. Okay, so this is good. So the signal rate, so S is low. S is actually the minimum. So this is actually also another advantage. So what are the cons? The cons here, or the disadvantages, are plenty actually. All the components that we talked about. So baseline wandering is really hard, right? Why? Because if you have consecutive ones, it's actually a straight line like this. So the baseline wandering tends to increase. Baseline wandering, remember, baseline wandering is actually the moving average of the signal. So as the signal goes up, the baseline wandering starts to go up. Okay. If you have straight zeros, again, the baseline wandering tends to go down. And as we said, the baseline, if it goes very high or if it goes very low, it increases the possibility of error. So this is bad. So if you have consecutive ones, you have straight voltage V. If you have consecutive 0, you have straight voltage of 0. And in both cases, it's bad. So baseline wandering is really high. DC component. DC component talks about the power. This is F. We need to know the power, the actual power at 0 frequency. At 0 frequency, when there is no change in the signal. Again, if there is positive voltage, if there is straight ones, okay, then the frequency is 0. What is the power in that case? The power in that case is double the or square of the voltage, so it's actually high. Okay, so you have a DC component here because it's the signal tends to have high power when you have consecutive ones. In other words, we should never have consecutive ones in the case of non-return to 0. So the DC component is also high. Okay. What about self-synchronization? Self-synchronization is really bad as well. you have no self-synchronization, because if you have straight ones or straight zeros, you don't have any transition or any change of the voltage that would indicate to you that the clock should really adjust itself to that boundary. So also no self-synchronization. There is no self-synchronization in that case. So the disadvantages for non-return to zero is really a lot. So all the phenomena that we talked about, they exist in the non-return to zero. But the good thing is that the signal rate is really low. The signal rate is really low, and it's simple. So as we will see, as we try to solve some of these problems later, we will see that we will start to get higher complexity in terms of the sender design or the receiver design. One thing to notice here is that the normalized power here is the power per bit. Is the power per bit. And this normalized power is actually the probability of having 1, okay, multiplied by the voltage level of 1. As we know, the voltage level of 1 is V. Okay, the voltage level of 1 is V. So the probability of having 1, if we assume that in general we have the same probability of having 1s as the zeros, so the probability of having 1 is half, the probability of having 0 is half. So it's half times the voltage level of 1, which is V squared, and half multiplied by the voltage level of 0, which is 0. So the normalized power is half V squared. Okay, so this is the power per bit. Okay, and this is relatively the normalized power is relatively low because of the fact that we use 0 voltage level to represent the 0. Okay, so this is the first line coding scheme we talk about in the category of unipolar, and this is the only one in the category of unipolar. For the polar, where we have positive voltage and negative voltage, both, okay, but we do not have 0. So in that case, we have two line coding schemes here. You have the non-return to 0 level. So the non-return to 0 level talks about the fact that instead of representing data elements, the 0 data element as 0, we represent it by negative voltage. So this is the only difference between the unipolar non-return to 0 and the polar non-return to 0. So polar non-return to 0 tends to represent 0 as positive and 1 as negative, or the other way around. So here, as we can see, the 0 is positive voltage and the 1 is negative voltage. Okay, 0 is positive and 1 is negative. So you can reverse, it's fine. Type. So what is the difference between this one and the non-return to 0 اللي هو the unipolar non-return to 0? So here we have negative voltage to represent one of the data elements. Type. What is the advantage of this? The only advantage for the non-return to 0 is the fact that it tries to improve, in terms of cons, it tries to improve the baseline. Why? Because if we think about consecutive zeros, for example, if you think about consecutive zeros, so the voltage level is always positive, right? Using this scheme, it's always positive, right? So which means that the baseline will start to increase. Okay, which is similar to the unipolar non-return to 0. The only difference here is that once you have 0, okay, if you have 0 here, it actually pushes the voltage level way down, okay, which allows the baseline to reduce very fast. Okay, so the big transition here, okay, is higher compared to the unipolar non-return to zero, in which case the baseline reduces a lot after having consecutive zeros or consecutive ones. Compared to, remember, the unipolar non-return to zero, if you have zero after consecutive ones, the voltage level is zero, in which case the baseline will not reduce drastically. It will continue for some time, and it reduces slowly. Okay, so in that case, the baseline wandering for non-return to zero unipolar reduces or goes down slower compared to the non-return to zero polar. So this is the main improvement that we have achieved, and in fact we have paid some cost for this. ايه بقى الكوست؟ حد عنده فكرة ايه الكوست؟ Can anyone يعني think about a disadvantage or a cost that I had to pay for the polar non-return to zero in order to reduce or in order to improve the baseline? حسين اتفضل. Okay. So in terms of power, if we assume again that the probability of having zero equal to the probability of having one, the power in that case is the probability of having zero, which is half, multiplied by the voltage level of zero, which is, again here, it's actually V squared. The probability of having one is also half, times the voltage level of having one, which is minus V squared. So here, the power is actually double, assuming that you have a big transition between the 1 and 0. So the big transition between the 1 and 0 allows you to improve the baseline wandering. However, this comes with an actual cost related to the power. ماشي. Other than that, having the baseline wandering reduced is good, but هل احنا did we fix anything related to DC component? No, we did not, because in fact the DC component here is higher, because again, if we have consecutive zeros, it's positive voltage. If you have consecutive ones, it's negative voltage. So the DC component here actually is 1. It's not half V square, it's actually 1 V square. Okay, so the DC component here is high, and also if you have consecutive ones and consecutive zeros, you have the same voltage level with a positive or negative, and there's no change. So again, the self-synchronization is not there, so there is no self-synchronization. طيب, here we have another variation of the same polar non-return to zero. It's called non-return to zero invert, and by that we mean that we will not take the absolute value of the voltage level as the indicator for its 1 or 0. What we will do here is that if you have 1, okay, then you toggle the voltage level, which means that the actual information to the receiver, whether this is 1 or 0, is actually here. Okay, it's actually in the transition. It's not here. Okay, so this indicates that this is 1. Why? Because the voltage level has dropped from positive to negative, which is toggle. If you have 0, then the voltage level stays the same. So again, if the voltage level here stays the same, okay, then this indicates 0. So it's not the absolute voltage level, it's actually the differentiation or the difference in the voltage level that indicates whether this is 1 or 0. So this is what we call non-return to zero invert. Type. What is the main advantage of inversion here? The concept of inversion, as we will see later, it's actually used a lot. And the concept of inversion always helps to increase the transition of voltage levels. And as we have discussed before, maintaining the same voltage level for a long period of time is always bad, right? Especially if it's positive or negative, because it increases again the baseline wandering, it increases the DC component, and it actually maintains no self-synchronization. So inversion here helps to add or increase more transitions in the voltage level, and that's always good. So if we go back here and if we look at the cases where you have straight zeros or consecutive zeros, so in that case, so if you have consecutive zeros, so you have fixed voltage level. So if you have straight zeros, straight zero means that the voltage level does not change. So if you have 0, 0, 0, 0, 0, 0, so the voltage level stays the same. Okay. So what about if you have 1, 1, 1, 1, 1, 1, 1? So for the case of polar non-return to zero L, this ones will create negative voltage all the way, right? However, in the non-return to zero invert, it will start with negative, and then here 1 means toggle. So toggle means that you go positive, okay? And then 1, so you toggle. Then 1, you toggle. Then 1, you toggle, and so on, okay? So in that case, we have introduced more transitions for the case of consecutive ones, and that's actually good. So it at least it solves the problem of maintaining the same voltage level for 50% of the cases. So for the consecutive ones, it's still the same, but for consecutive zeros, it is actually improved. So, sorry, or the other way around. For consecutive ones, it's actually improved because 1 means toggle, right? So the concept of inversion is always good to be introduced. However, the cost for this is what? حد عنده فكرة؟ You have to understand that there's no free lunch. Nothing in this world is for free. Okay? So you have to think about, if you have gained something, what did you pay? Okay? What is the cost here? حد عنده فكرة؟ Yes, Magid. لا هو الانرجي stays the same. Energy stays the same. But there's something. ايوه سليمان. سليمان اتفضل. يعني ايه more equipment؟ مش فاهم. يعني ليه cost increases يعني؟ مش فاهم يعني ايه more equipment او ايه cost increases؟ انا بقول لك what is that cost؟ ايه الكوست اللي انا دفعته؟ اتس بيت ايه؟ لا مش واضح، لا مش واضح. لا هو so the cost here is actually in fact more complexity at the sender and the receiver side. يعني at the transceiver. The transceiver itself, transceiver اللي هو transmitter and the receiver, they have more why more complexity? Because now the receiver, in order to generate at the sender side, in order to generate the signal element, it has to look at the previous bit, okay, and the current bit, okay. It has to look at both in order to know whether there is a transition or not. Rather than for the polar non-return to zero L, if the signal is if the element is 0, I generate positive voltage. The element is 1, I generate negative voltage, regardless of what the previous bit is. So here I have to look at both the current and what's next. in order to generate the signal element. So if the current is 1 and the previous voltage is positive, then I have to turn to negative. If it's negative, I have to go to positive. And if it's 0, then if the current is positive, then it stays positive. If negative, it stays negative, and so on. So this adds more complexity on the transceiver at the transmitter side as well as at the receiver side, because also the receiver has to look at not only that, the receiver, in fact, it causes another slight problem called error propagation. Which means that if the receiver side interprets any bit in a wrong way, all the upcoming bits or many upcoming bits will be in error. Why? Because if this element is positive and it should be negative, or the other way around, then this will affect the upcoming bits, and you may in fact cause some errors repeatedly. So the inversion here, it has benefits, but there is a cost associated to it, at least the complexity side. ماشي؟ طيب. So for a polar return to 0, here we have negative voltage to represent the 0, positive voltage to represent the 1, but we in each signal element, we have to always return to 0. We always have to return to 0. So so in the middle of the bit, we have to always go back to 0. But remember here, despite the fact that this has 0 voltage level, the 0 here, it's not meant to represent any data elements, right? So in all bits, you have to return to 0. Type. What is the advantage of this? The advantage of this is to fix all the problems that we have talked about. So here, in terms of pros, all the problems that we have talked about are actually gone in a way. So the baseline wandering is actually very low, right? Because in each bit you always return to 0. So this tries to keep the baseline really close to the 0 as much as possible, right? So you always go back to 0, always go back to 0. So this maintains the baseline wandering to be around the 0 most of the time. So DC component is not there because again, you have positive and negative, but you always go back to 0. So you never have a fixed voltage level with a frequency of 0. So DC component is actually very low. And you have طبعا self-synchronization is there because you have transition in the middle of the bit. So what is the cost here يا شباب? The cost here is clear بقى. What is the cost? أي حد يقول يعني this is easy يعني. So what is the cost here? Very high signal element, very high signal rate. Why? Because the R here, R is the number of bit elements, which is 1, over the number of signal elements. You have 2 signal elements to represent each bit. Okay, so here the signal rate is half times n times 1 over R, which is 1 over half. So this is actually n. So the average signal rate here is double all the schemes that we have talked about before. Okay, so the signal rate here is double. So if you want to improve on the baseline wandering and the DC component and self synchronization, so on, you have to pay cost. You have to pay a cost. واضح كده؟ So this is non-return to 0. Type. Within the same polar category, we have the biphase. The biphase is what we have talked about before in network 1, which is the Manchester encoding. The Manchester encoding here tries to use the polar concept. So you have positive and negative, and it tries to eliminate the 0. Okay, so the one of the cons here is that the transceiver here is simpler compared to the return to 0, because the return to 0 has positive, negative, and zero. Here we don't have zero. Okay, so here we have only a positive and negative. And we said that for the polar category, if we have the a zero, it's not a to represent data elements. So here we actually eliminated the zero. The signal rate is still the same, right? Is n compared to the return to zero. So it's good. It's good in a way because we maintained all the transition in the middle of the bit, which helps us to improve on all the three criteria that we have talked about. Baseline wandering, DC component. There's no DC component here because you always have transition. So you have zero, you have no zero frequency component in this signal at all. So here you have zero power at frequency 0, right? So there's no DC component, baseline wandering is improved, and of course self-synchronization is very good. Okay? In fact, you have the advantage of the fact that it's the same signal. It's the same signal and it's mirrored. So it's the same signal but with phase shift 180 degrees. And that actually improves the complexity of the transceiver. So the complexity of the transceiver has one signal and it actually mirrors the signal for 0 or for the 1. Okay, so this improves compared to the non-return to 0. It's simpler because it deals with 2 signal levels best, not 3. And of course, it's the same signal for 0 or 1, but it's mirrored. Okay, كده يا شباب. طيب, what is the differential? Differential Manchester tries again to use the concept of inversion. So again, it's not the 0 and the 1 that decides what signal of these to use. It's not the actual bit. Okay, so the actual bit again controls the transition. Here, the transition here. So the actual bit controls the transition. So if you have 1, then the voltage level stays the same and then invert. If you have 0, then invert and then invert. Okay, so you have two toggles for the case of 0, 1 toggle for the case of 1. So for the case of 1, the voltage level stays the same and then you toggle. Okay, for the case of 0, you toggle and then you toggle. You have 2 toggles for the case of 0. So again, so the differential Manchester does not have any added advantage compared to the normal Manchester encoding, actually, other than the fact that you use the bit to control the transition, okay, of the voltage level between each bit and the other. Okay. So any questions so far, ya shabab? Type 4 for bipolar, again, so just to be able to follow what we're talking about so far. So we talked about unipolar. Unipolar, all the voltage level are either positive or 0, okay, or negative or 0, but there's no positive and negative. Okay, polar talks about positive and negative, and 0 is never used to represent the data elements. It's never used to represent data elements. Okay. The bipolar here talks about the fact that we use positive, negative, and 0 all to represent data elements. All to represent data elements. So you have here in this category you have what we call alternate mark inversion. So this alternate mark inversion, or AMI, tries to work on non-return to 0. They say, okay, so non-return to 0, remember, for non-return to 0, we had a very powerful advantage, which is the signal rate is actually n/2. Okay, so that's the limit, or this is the minimum limit that Nyquist has told us to be able to represent the signal efficiently. But we had DC component, we had baseline wandering, we had no self-synchronization, and so on. Can we maintain the same signal rates n over 2 and try to solve these criteria اللي هما these matrix البيزلاين wandering وكده. So they come up with a very nice idea. They said that the like non-return to zero, we will use the zero voltage to represent the zero. Okay, so that's normal. So when we have zero, consecutive zeros, we have zero voltage. So this has no self-synchronization. We understand that. We know this. If we have one, okay, then the first we have positive voltage. If we have another one, then we have to go back, okay, to see what is the last non-zero voltage level. If it's positive, we'll make it negative. If it's negative, we'll make it positive. واضح? So it tries to use the polar to try to balance out the positive with the negative. You try to maintain balance between the positive and the negative. Okay? طيب, in terms of signal rate, this is similar to the non-return to zero. So you have R, the ratio of R is actually is 1. So R equals to 1 because you have one data element and one signal element. Okay? So R is 1, which means that the S is n over 2. That's good, right? Type. Do we have any DC component? Let's see. If we have consecutive zeros, it's zero voltage level, صح? So the zero voltage level has a power of 0, right? So we do not have a positive voltage or positive power. In the case of, there's always positive power, but you don't have power, you don't have high power when you have consecutive zeros. So if you have consecutive ones, then what will happen is that you will have like this. So you will have 1 positive, and then 1 you go negative, and then 1 you go positive, and then 1 you go negative, and then 1 you go positive, and so on, right? So if you have consecutive ones, you don't have any zero frequency in that case. So in fact, you have no DC component in this case, okay? Because for the case of consecutive zeros, it's a zero voltage. For the case of consecutive ones, it always toggles. So you have no zero frequency at all. So we have improved on the DC component. So in terms of advantages, one, the DC component is vanished. That's good. Okay. What about baseline wandering? Baseline wandering is also improved. Why? Because again, if you have consecutive ones, you always toggle, so you keep the baseline wandering around the zero voltage. Okay, so baseline wandering has improved, at least for the case of consecutive ones. Okay. Self-synchronization, well, self-synchronization, يعني, it's not completely there. Why? Because for the case of consecutive zeros, you have zero voltage, you have fixed voltage level, so you have no transition. Okay, so this, يعني, it's better, at least for the case of consecutive ones, because for the case of consecutive ones, you have transitions. For the case of consecutive zeros, you have no transitions. So self-synchronization has improved 50% of the time. واضح كده يا شباب? Any questions so far? So the AMI has improved a lot compared to the non-return to zero, improved the DC component, improved the baseline wandering, improved partially at least the self-synchronization, and it maintained the signal level the same. Isn't that beautiful? So that's actually good. طيب, what is بقى the so this is pros and pros. What is, in terms of cons بقى, what is the What is the disadvantage here? Yes, Daniel. Yes. So so here, in order to generate the signal element for this one, I have to go back not bad to this or this. I have to go back all the way. I have to go back 3, 4 values until I hit a voltage level that's not zero. Okay, because I need to know whether this is positive, so to make it negative, or if it's negative, I make it positive. So definitely, in terms of complexity, the complexity of the transceiver is really high. Okay, so I don't only rely on the current bit or the bit before. I actually may have to go back several bits in order to see what is the last non-zero voltage in order to generate the signal element for the current bit. So that actually increases the complexity of the transceiver. Okay. The pseudo ternary is nothing but يعني the reverse. يعني so it's so the one here is zero voltage and the zero alternates. So you either use the one or the zero to alternate. So the pseudo ternary is not actually new. It's the same MI, but it's the opposite. So until now we finished the unipolar, we finished the polar and bipolar. Right? So we finished all these 3 categories. So now we have the multi-level. So for the multi-level, we have arbitrary number of signal elements and arbitrary number of levels, okay, to represent the incoming bit elements. So here we have in general m bit elements, okay, and we know that each bit element is binary, so it's either 0 or 1. Okay, so if you have m bit elements, each one is binary, so you have 0 or 1. What is the number of combinations that you have? What is the number of combinations that you have, ya shabab? Anyone can answer, yani. What is the number of combinations if you have m bit elements? Each one of them is binary. 2 to the power m, bro. Yes, sir. So you have 2 to the power m different combinations. تمام. تمام. طيب. You have بقى n different signal elements. Each signal element has L different levels. So if you have imagine if n is 1, which means that you have one signal element, and you have L different voltage levels. So for example, we talked about that before. You can use 4 signal levels, okay, to represent 2 binary bits. صح? You have 0 0 0 1 1 0 1 1. So you can have L equal 4 to represent 2 bits. We talked about that before, right? So L equal 4 will allow us to represent 2 bits. So for L equal 4, we can have M equal 2, right? So this is L different levels. Type. If we have two signal elements, each of them has L levels. What is the number of combinations in terms of signal elements here? لا العكس بقى. Yeah, because remember L here is the number of levels in one signal element. Okay, so if you have 2, this will give you a لا لا how many combinations can you have if you have two signal elements, each of them has L? So it's actually L square. هي it's the same يا شباب, it's the same. انت عندك هنا for the number of bits, okay, if you want to know the number of combinations, then it's the number of bits that you have, okay. The states of single bit is A. The state of one single bit is either 1 or 0. So you have two possible states. Here you have L different states for the same voltage element, for the same signal element. You have L different states, okay? So if you have two of these signal elements, this will give you square L. If you have three different signal elements, so this will make it a L to the power 3. If you have four signal elements, then this will make it 4, and so on. In other words, the number of combinations in terms of signal elements, okay, if you have arbitrary number of signal elements, each of them is L levels, is in fact L to the power n, okay? So here we have the number of signal element combinations is L to the power n, okay? The question now is, what is the relationship between the number of signal element combinations and the number of bit element combinations? Is it equal, greater than, less than? If we have number of bit element combinations more than the signal element combinations, can we have a valid line coding schemes? No, because we have number of bit element combinations more than the signal elements that we have. We can never have this. So either we can be equal, or it has to be more on the signal element combinations, right? So we need to have more signal elements more than the bit element. طيب, why do we need to have it more? طب ما have it equal all the time. طب ما we can say the number of signal element combinations is always equal to the number of bit element combinations. Similar to اللي هو when we said that we have 0 0 0 1 1 0 1 1, and we said that we will use different voltage level to indicate each of these bits. So this is, for example, 2V, V, minus V, minus 2V مثلا. So we have 4 different voltage levels, okay? So in that case, L is 4 and M is 2, and they are equal, right? So why do we need to have it more? Is it really good to have it more? In fact, yes. And we will see بقى, if it's more, this gives us a more degree of freedom that we will use it for our benefit. We will use it for our benefit. How? To improve بقى on all the three phenomena that we talked about: the DC wandering, the baseline wandering, the DC component, and the self-synchronization. So we will type. So this is the convention for the naming for the multi-level schemes. So the B here is fixed. So for example, if you have two bits, each bit is binary, okay, and you have L equal 4. In practice, L equal 4, we call it quaternary. So in many cases in practice, they remove the L letter and they replace it by either binary to represent two voltage levels, similar to the two possible states for the bit 0 or 1. Ternary, if you have three voltage levels, similar to مثلا AMI. AMI has a positive, negative, and 0. So that's ternary, okay? And quaternary, it indicates 4 different voltage levels, okay? So in many cases, we only need 4 voltage levels, but we can increase the number of signal elements, as we will see. So, in fact, this scheme is 2B1Q. Okay, so it's one signal element that has 4 different voltage levels to represent 2 bits. So M is equal to, and bits is binary. So this is in fact line coding scheme that we will talk about in this category, which is the multi-level. So for the multi-level, this technique is not new. So we talked about this before. So now we get to analyze that technique based on the concepts that we have learned so far. So we have 2B1Q. So each 2 bits are represented by one signal element. So here the 2 constraints are exactly equal. Okay, so you have 4 different voltage levels for each signal element, and you have only one signal element to represent the bit pattern, right? So L is 4 and N is 1. Okay, and for the bit elements, you have each 2 bits represented by one signal level. So it's equal, right? So let's see when it's equal, what we will get in terms of, again, in terms of the baseline one-ring DC component and the self-synchronization, so on. And I want you to focus on this part only for now. Okay? So forget about this column. I will talk to you about this column in a minute, but let's focus on this. So here, simply what we have is that the 0, 0 will be represented by positive voltage of 1. The 0, 1, positive voltage of 3. 1, 0, negative voltage of 1. 1, 1 is negative voltage of 3. Right? Type. So this is good. In terms of signal rate, again, this hits the Nyquist limit, because here, remember, we are talking about 4 different voltage levels. So the signal element is again C, assuming that C is half, okay, times N times 1 over R. What's R بقى here? What's R? R is the number of data elements, 2, divided by the number of signal elements, which is 1. So R here is 2, and this is half, so it's actually N over 4. And again, we hit the Nyquist limit here, because for 4 voltage levels, this is the lowest signal rate you can get. Okay, that's what Nyquist has told us. This is for the roughest approximation that we talked about. Type. So the signal rate is very good. It seems attractive. But what about the baseline one-ring DC component self-synchronization? In fact, all of these, they exist, big deal in this scheme. So here, not only do we have fixed voltage levels for consecutive zeros and consecutive ones, we have the fixed voltage levels for the case of 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. We have the same voltage level for the case of 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Right? So if you keep the same pattern here repeatedly, you get the same voltage level. And again, the same voltage level for a long period of time is bad, right? Because it causes baseline one-ring, it causes DC component, okay? And it has no self-synchronization. And that's why here you have clear DC component here, right? The DC component here is high, right? So the baseline one-ring still exists. If you have the same pattern repeatedly, then again you have baseline one-ring. You have no self-synchronization because you have no transition in the signal that gives you any information to adjust your clock. So again, the self-synchronization is not there. So is it really that bad? They try to use the concept of inversion here again. The concept of inversion here, they try to use it to improve the situation 50% of the time. Similar to what we have done for the non-return to zero inversion, if you remember. So what happens here is that they say, so we will add another column here to use the concept of inversion. So if the previous voltage level is negative, okay, then we will not take the voltage level from this column, we switch to that column. And what happens in that column is that everything is inverted, as you can see here. So what the 1 becomes -1, and the 3 becomes -3, and the -1 becomes 1, and the -3 becomes 3. The reason for this is that if you have consecutive zeros, then you have +1 voltage all the way. If you have consecutive 0, 1, then you have positive +3 all the way. If you have consecutive ones, okay, then let's see. If you have consecutive ones, let's see, we have 1, 1, and then 1, 1, and then 1, 1, and then 1, 1, and then 1, 1, and so on. Okay? So for the first 1, 1, we will say, okay, so it's -3. So we will go -3. Okay? Then it's 1, 1. Here, because the voltage level is negative, we will have to switch to the other column. And the other column tells you that the 1, 1 is actually +3. So we will toggle to +3. Okay? And then we will toggle to -3. And then we will toggle to +3, and so on. So here, if we have consecutive ones or consecutive 1 zeros, okay, we have alternation in the signal. So the inversion, the concept of inversion, allowed us to improve the situation by having more transitions, okay, at least 50% of the time, which is good. This is good improvement. Again, the cost is what is the cost? More complexity. More complexity on the transceiver design. Why? Because the transceiver design has to always look for the previous, what is the previous signal element? So I need to toggle it. Okay? So slight more complexity. And it's not that major, but slight more complexity. But this fixes the baseline wandering, DC component, self-synchronization at least 50% of the time. ماشي كده يا شباب؟ So for the case of consecutive ones, or the case of consecutive 1 zeros, the voltage level is 0, so the voltage level is negative, sorry, which means that you have to toggle. Any question يا شباب so far? So this is the first scheme for the multi, and this is based on the equal. So the constraint here is barely fulfilled. So 2 to the power m equals to L to the power n. Equals. Okay? طيب, if we have بقى كده, if we have the number of signal element combination more than the number of bit element combination, what is the advantage of this, and what is the cost that we have to pay? What is the advantage and what is the cost? So we have this technique, which is 8B 6 ternary. So here L is the number of voltage levels is actually 3. Ternary here is 3. So as you can see, you have negative voltage, 0 voltage, and positive voltage. Okay, so this is the L. And you have 6 signal elements of these. So you have 1, 2, 3, 4, 5, 6. Okay, so you have 6 signal elements. Each of them has 3 voltage levels. And we are trying to use this to represent 8 bits. Each one is binary. Okay, so here the number of bit element combinations is 2 to the power 8, which is 256, as we know. 3 to the power 6, which is the L to the power n, is actually as you can see, it's 478, which is a lot more than 256. Okay. So it's a lot more. So what is the cost that I paid here? It's more signal element combinations, of course. So this reflects on two things. First, the complexity of the transceiver, because the transceiver has to generate more signal element combinations, of course, and also the signal rate. The signal rate is higher, right? Because more signal elements means more signal rate, of course. So the signal rate here, assuming that C equal to half, is half times N times 1 over R. What's R يا شباب? Again, R is blindly كده the number of bits here, the number of bit elements divided by the number of signal elements. So it's actually 8 divided by 3, divided by 6, sorry. Okay, the number of signal elements is 6, the number of bit elements is 8, right? Which is 4 over 3. Okay, so this is a 3n over 4. This assumes that the C is half. For this technique, by the way, they use certain techniques to improve the C here. Okay, so as you will see later that this is actually 3n over 8, not 3n over 4. So they improve the C even more. Anyway, so for us, C is given, so we don't care. So let's see if we have more signal combinations more than the bit combinations. What can we benefit from this? We can benefit from this that we can actually avoid all the signal elements that have fixed voltage level for a long period of time. We can, in fact, balance the positive and the negative voltage levels. Okay? So we can avoid the signal element combinations that has more positives than the negatives, or more negatives than the positives. So we always try to maintain the negative and the positive. Why? Because again, this maintains the baseline wandering, it improves the baseline wandering, and of course it eliminates all the zero frequency components. Okay, and if it has transitions like this, then you have self-synchronization, which is good, right? So in this technique, what they do is that they say, okay, so if it happens that the number of positive voltage levels is more than the negative, or the negative is more than the positive, like for example here. So here, for example, you have 1, 2 negative, 1, 2 positive. This is good. This is balanced. If you have here 1, 2 negative, but 1, 2, 3 positive. Okay, so in that case, the next signal element you can invert. Okay, and the receiver has to be aware of this. By doing this inversion, again, we can improve the number of transitions and keep the baseline wandering around the zero all the time, which is good, because then we try to improve the error probability. We lower the error probability at the receiver side. Okay, so again, so the more signal element combinations gives us more degrees of freedom, that we will try to use the signal element combinations that maintains the positives and the negatives at the same rate, so that we have always baseline around the zero, and we improve on the transition, so we always have positive and negative equal. Okay, and this really tries to improve or lowers the error probability. ماشي كده؟ So this is the multi-level, which is called 8B16. Okay. Another multi-level scheme, which is, in fact, this is used for Ethernet. So this is the line coding schemes that are used for high gigabit Ethernet. So for high gigabit Ethernet, what happens, as we have told you before, that we have 8 different wires, right? For UTP, UTP has So UTP, unshielded twisted pair, has 8 wires, right? So it turns out for these 8 wires, 4 of them اللي هم دول they are used to represent data, actual data, and the other 4 are used for control signals. They are not used for representing actual data, for actual data elements, right? So for this, we use 4-dimensional signal elements. So we use 1, 2, 3, 4 signal elements. So n equals 4. Okay? We use L, we use the number of voltage levels here, 5, although the 0 voltage is not there. So we eliminate the 0 خالص. So we only have 4. So L here equals 4. Okay? So L equals 4, and the number of signal elements is 4. Another thing that we use here is the fact that each طبعا wire is separate from the other. So for each wire we use 4 different voltage levels. Okay? So if we calculate the signal rate here, if we assume that C is equal to half, okay, so C times N times, what is the value of R? R here is 8 different bit elements, so R is equal to 8 divided by the number of signal elements. It's 1, 2, 3, 4. So it's 4. So R is equals to 2, right? So which means that this is n over 4. Okay? This is assuming that C is equals to half. What happens is that because of the fact that the other 4 wires are used for control signals, they actually tend to reduce the probability of error really low using these control signals. Okay? So in fact, C is 1 over 4, not 1 over 2. So here it tends to be n over 8. And that's why, assuming that if you notice that the signal rate here is 125 megabaud, whereas the bit rate here is 1 gigabits per second. So someone might ask, this is in fact n over 8, not n over 4. But you have taught us the fact that C is always half. In fact, in practice, C is not always half. C can be 1 over 4, or can be any value, or 1 over 3. So in practice, they try to use lower values of C, but this requires extra techniques for error detection and correction. Okay? طبعا احنا we will not get to that, but احنا actually in the exam I will always give you C. I will not allow you to guess what is the value of C. So the value of C is always given, right? So here the value of C for this particular technique is actually 1 over 4. It's not 1 over 2. Okay? And in the next technique, as we'll see, is 1 over 3. It's not 1 over 2. So this is برضو the multi-level. So type last one which we'll talk about today is called multi-transition. The multi-transition technique again tries to use the transition to represent the bit, not the actual voltage level. So for the multi-transition here, if you have 0, then if you have consecutive zeros, then the voltage level will stay the same. سواء 0 or positive or negative will stay the same. Okay? If you have 1, okay? If you have 1, if the next bit is 1 and the voltage level is positive or negative, make it 0. So a case like this is this, for example. This voltage level is positive and the upcoming bit is 1. Okay, so the value is positive, make it 0. The value is negative, make it 0. Okay, if the next bit is 1, but the current level is 0, then a case like this, yeah, is this one. If the incoming bit is 1 and the previous bit is 0, then the 1 needs to be positive or negative. So make it positive or negative. We have to go back. So we have to go all the way back to see what is the last non-zero element. It's negative, so make it positive. If it's positive, make it negative. So this is a complete logic which you need to memorize and apply it carefully. And the only reason for the multi-transition or MLT3 is this scenario. If you have consecutive ones, it's a very interesting signal that will get generated. Very interesting signal using this logic. Because the first one will be positive, and then you have 1. If you have 1 and you have non-zero voltage, then go to 0. Then 1. Then this one, we will have to go positive or negative. So positive or negative, so we have to go back to this positive, so make it negative. Okay? And then we have incoming 1, so we are non-zero, so we go to 0. If we have 1, then we are 0, so we have to go toggle to the previous non-zero, so it's positive, and so on. So if you have consecutive ones, you have this very interesting signal. So what is interesting about this signal is that you can, in fact, use a sine wave like this to represent this signal. So each four bits will be represented by one cycle of sine wave. Okay? Which means here is that for this extreme case, the signal rate is actually n over 4. For the extreme case of consecutive ones, the signal rate is n over 4. Okay? So, of course, not all the time you have consecutive ones. So in that case, they keep the C at 1 over 3, which means that the value of n, the value of signal rate is in fact n over 3. Okay? By having this complicated logic. Again, the cost is a complexity. So we have paid some cost on the complexity by carefully designing the transition between the ones and zeros in a very careful way like this. We have improved the signal rate, okay, but we have added some complexity in terms of the transceiver design. So this is the multi-transition. So this table summarizes all the techniques that we have talked about, and this table is actually very important. So you can look at it and make it like a reference to compare between all these techniques at the same time. Okay, Shabab? Any questions? Any questions here? So as I said at the beginning of the lecture, we have the quiz on Wednesday, inshallah. So next class we will have the quiz. We will start with the quiz at sharp at 11, and then we will continue the lecture, inshallah. So don't forget to take attendance. تفضل. ها؟ تفضل.